So, this is just to recall what we have discussed so far. Previously, we have discussed what is the meaning of several variable functions, and we can see we have seen that there are many functions. In fact, most of the functions in real life are actually several variable functions. They have more than one independent variables. There can be two independent variables. There can be three independent variables. There can be n different independent variables. For this n is actually uh, n is integer, a positive number. N can be 100, it can be 1000, it can be 10,000 also. Okay, but n is less than infinity. I mean, we don't have infinite number of variables, but whatever we have, finite. It can be one lakh or 1 crore. There can be 1 crore variable, but whatever may be the large number, it is not infinite. It is always finite. So finite, any number is finite, meaning n is strictly less than infinity. Then we have defined the definition of a limit in terms of a function of a several variable. And then we have seen that if the x comma y approaches to a comma b, then f of xy equals to said to be L as we have seen the epsilon delta definition. Okay. The meaning is fxy will approach to L as x comma y approaches to a comma b. That particular point. So at that point, the limit at a b of this function fx is L. Similarly, the continuity also defined as f of x comma y is continuous at the point a comma b, then the limit value and the functional value will be same. They will be equal. Now, if this happens for all the a comma b point on the domain that we are defining the function, then f is continuous on the whole domain. This is one we have mentioned and we have seen also. And then we have defined the partial derivative with respect to x and also with respect to y. So for that we have assumed y as constant and then partial derivative we have calculated. So del x is defined as h goes to 0, x plus h, and y is constant here. Y is constant. You can see here. Only changes, x is only changing. Okay. And the difference as h goes to 0, then this would be called as partial derivative with respect to x. Similarly, we define partial derivative with respect to y. Okay. Now, what would be the geometrical significance of the partial derivative with respect to x and with respect to y? If you try to recall, okay, just to recall, for if we have ordinary differential equations, ordinary derivative, what we have seen, this represents the rate of change, or it will represent the slope of the tangent. at a given point P. So here we know that. Now we have also seen that these are nothing but the slope of the tangent along the x-axis. If you draw the curve for particular after fixing, okay. So they will also represent the. In fact, we will discuss more in this. What is the significance of? Now we have defined. Now if you try to define more derivatives, which is called a higher order partial derivatives, in how, in this way, for example, from now onwards, this there is a notation, we can call it fx with respect to derivative with respect to x. It can be denoted by f of y. Okay, then we can define it in this form. Okay, so this is actually the working formula will look like of this form. Suppose we substitute here, because this is x actually and this is y. So del x with respect to del f del y. Okay, this is given by limit h goes to 0. This is fy. Okay, of a plus h comma b. They are calculating at a comma b. Okay, so let us just write x plus h. You can write here x plus y. Again, y is constant, or you can write x naught plus h, y naught minus a2. That means fy x naught y naught h. Then this derivative is called actually del to ef del x del y. Similarly, you can define del x del f del x. There you get limit h goes to 0, then f of x of x naught plus h comma y naught minus fx x naught y naught divided by h. Similarly, you can also define here del y del to f. Sorry. So this would be denoted by del to f del x2 del x. Okay. So this is again denoted by limit. Okay. With respect to y, so let us take k equals to 0. And in place of this function, it will be, so here if you can write, if inside a derivative, partial derivative is y with respect to y, then we will have y. So x naught comma y naught plus k minus f of x naught comma y naught. And here we get k. Similarly, you can also define del 2 here del y2, which is nothing but limit k goes to 0 f of y x naught comma y naught plus k plus f of y x naught y naught divided by k. So we can see it is possible to find out higher order partial derivatives. So this is again, it can be denoted as fxy, and here it can be defined as del to f del y del x. So this is also not denoted as fyx. So the definition from the limit, and here it can be defined as fxx. Sorry, if xx is here it is fyy. Okay, so we have found these variables. In fact, hereafter you can also define del 2f or del 3 if possible. The derivatives are there, then also you can define. So del y3. So in that case, you take the limit k goes to 0, and then here you take fyy, and so on. You can take them. Similarly, you can define. Okay. So these are the, if higher order possible, higher order derivatives are possible, then we can define them symbolically of this form. In fact, there can be possible fxx, x, fy, x. It can also be possible, or you can also define fy x2. That means in that case, fy. Let me write fy x actually, which is nothing but del y del to f del x2 type. So of this form, there are several possible combinations can be there. Now, provided the limit should exist, then only you can say this derivative is possible. Now, question remains that whether fxy at x naught y naught is equal to f of y, okay, if yx. These are called mixed partial derivatives. because we are differentiating with respect to x and y, one after another. Let me write them, the mixed partial derivatives. The question remains that whether they are equal. In fact, they are, in general, they are not equal. They will be equal when they have they will satisfy the continuity property. In fact, if you check the limiting definition here, you will get these values. Try to verify. And when they will be equal, so there is a theorem called mixed derivative theorem. So in this theorem, it is said that when all the derivatives or the first order derivative, first order partial derivatives, and the second order partial derivatives are defined throughout the region, and also they are continuous at that point. Okay. At that particular point, they should be continuous. Otherwise, it is not possible to equal. So, if they are continuous, then only we can claim that this is equal. So, this theorem is very important because normally what people do, they will try to do the derivative with respect to as usual we do for ordinary derivative. They will follow that method, and without understanding, they will write these two are equal. But this is not the case. It is not always true. There is a counter example. This is a counter example that they are not equal in general. Now, for more higher order partial derivatives, as I said, we can define several partial derivatives and so on. But this type of derivatives are uh, important for our mathematical practices. But in real life, we may need such kind of derivatives. For example, studying the heat equation, one-dimensional wave equation, and so on. So multi. Okay. So here is a simple problem. If you try to solve it, so prove that y equals to f of x plus at is given, and okay, f of x plus at plus g of x minus at, it is given. Now you have to satisfy this equation, provided a is to be any constant. So here it is y equals to f of x plus at is given, mine plus g of x minus at. Then differentiate, partial differentiation with respect to x. It will give del y. Okay. Here the independent variables are x and t. Independent variable. And y is our dependent variable. So we have to do this derivative. As usual, we can do it. So this is going to be f dash of x plus at plus g dash of x minus at. Now if you differentiate again, del 2y del x2, so you will get f double dash x plus at plus g dash x minus at. Similarly, you can differentiate with respect to t del y del t. So this is going to be with respect to x t, so x plus at into, there will be one a, because it is multiplied with t, no? So chain rule, apply the chain rule. So this would be g dash of x minus at, and there will be minus a, and del 2y dt2, sorry, del t2. So this is going to be f double dash x plus a t into a square plus g double dash of x minus a into t, which is again minus of minus, it becomes plus, so a square. Now this is nothing but we can take a square common. From there we have f double dash of x plus at plus g double dash x minus at. So if you call this one as equation 1 and this is 2, so from 1 and 2 we get del 2, okay, del 2y del t2 equals to a square times del 2y del x2. Hence we have proved the claim. So this is our target. So the computation is not that much difficult. It is just we have to take one variable at a time, constant, and differentiate with respect to the other constant. Sorry, other variable. Now, if we have a function x, y, z, in that case, what we will have? We will have w. In fact, in case of this, we will have fx first, then fy, and fz. So that means when we differentiate with respect to x, so other two variables are constant. Similarly, you can have fx, y, z, and there will be many combinations. But we have to be careful. Now, for another example, if you try to find out the relation whether this is true or not. Let us verify. So z is given x square tan inverse y by x minus y square tan inverse x by y. So differentiate with respect to partial derivative. We will get so with respect to x we will get here. So first this one, so u into v formula. So this is 2x times tan inverse y by x. Then we have plus, so x square will be constant now, and then we have tan inverse y by x. So what it will be? 1 by 1 plus y square by x square. But we are differentiating with respect to x, and this y is constant now. So 1 by x is there. So for that we will have again y by x square. And then we have only x square. So minus y square into tan inverse of x square, that will be 1 by 1 plus x square y square into, so differentiate with respect to x, so this would be 1 by y. Now if you try to simplify, let us do it. So this is going to be 2x tan inverse y x y by x plus, so this is x square, again we have, here is also x square, so this one and that one will get cancelled. So we have here negative x square into y. Then if we do this simplification, so x square plus y square, and then finally we have, this is minus y, y square, and then another y will be here, so this would be y cube by x square plus y square. Okay. So if you just try to simplify more, 2x tan inverse y by x. So here x square plus y square is there. So let us take minus y, take y common, y times, you have x square plus y square divided by again x square plus y square. So this one will become 1. So finally we have 2x tan inverse y by x minus y. Now again if you differentiate with respect to, again, partial derivative with respect to x, okay, now again, not again, now partial derivative with respect to y, because we have to find out this one. So whenever you find this, the order is very important. Okay. So the meaning of this one is actually So y is first, so that means del y, and inside coefficient will be this del z del x. So that is why we have to first differentiate with respect to x and then y. So now we have this one. Now next we try to find out. So del y del z del x. So this is nothing but del to z del y del x. This is nothing del y, and the inside function is 2x tan inverse y by x minus y. So if you do this differentiation, then you will get here 2x is there. So 1 upon 1 plus y square by x square. Since we are differentiating with respect to y, so there will be 1 by x will be there. Multiplication. Okay. And then for this y, it will be 1. Now what we are having, so this x will be getting cancelled, and the numerator will be 2 by x square plus y square. Sorry, this is different. So 1x will be cancelled, 2x square will be there. So this x and that x will be cancelled. So here we have 2 times x square by x square plus y square minus 1. So now if you simplify more, so 2x square minus x square minus y square divided by x square plus y square. So this is nothing but x square minus y square by x square plus y square. So this is what we have to prove, del to z del y del x. So whatever we have done for ordinary differential calculus, for ordinary derivatives, same idea, but we have to think of the other variable as a constant. Now if you try to find out the derivative for this function, then we will have of this form. So u equals to e to the power x y z. Okay. So del u del x del u del z, because you want to find out, okay, this order. So if you want to find out this order, so that means the order is del x del y, then del z, so del u del z. So this is the actual order. So we have to find out first this inside partial derivative, then we go for this one, and finally this one. So 1, this is 2, and this is 3. So for 1 we have to find out this one, del z. So for this, what we will have, so e power xyz into, because we are differentiating with respect to z, so the constant term x into y will be there. Similarly, if you try to differentiate with respect to y, so del 2 del y del del u del z. So this is nothing but del 2 u del y del z. So this is differentiation with respect to partial derivative with respect to y, and here we have e power xyz into x into y. So this is again we have to find out e power x y z into x into y. That means we will have only x. Okay, Satyam is asking, sir, should we follow the order when differentiating with respect to different variables? Actually, Satyam, the thing is, you have to look at the target. Okay. Based on that, you have to do the differentiation. Because as I said, that f of xy, fxy at some point may not be equal to f of yx at the same point. So this order is very important. You cannot just say since uh, del 2 f del x del y or del 2 f del y del x, they are equal, because you don't know, or we don't know whether this limit they will exist and they will be equal or not. In fact, the problem that I have given you, for that the limit is actually sometimes it is minus 1 and then 1. So that is why this order is very important. Which order we are differentiating, in which order. So that's very important to keep in mind. If you do in the reverse order, then you may get a different answer. Maybe the different, whatever, you may get something, but that may not be asked. Okay, so that is why it is important to follow the order. So in which order the question is given. Okay, so from now we have to find out the other quantities. So this is again xy e power xyz. So here you will get that xy is constant then, and you are differentiating this one. So for that again the another quantity will be there, which is xy, and there will be xz, which is nothing but e power xyz y into x plus x square yz. So finally, if you do this, the last part, then del cube u, del 3u, del x, del y, del z. This is again, so del x with respect to, okay, x, so x y z, x plus x square y z, and try to verify. This is nothing but e power x y z into 1 plus 3xyz plus x square y square z square. Do these steps, verify it, and there are some practice problems. try to verify them. Okay. Okay, so now the geometrical significance that I wanted to tell you. So let us inform about the geometrical significance. What is the meaning of geometrical significance? So as you remember that if you draw a tangent line, if you remember the functions that we have discussed in one variable case, at P, if you define one tangent, okay, then the derivative will be the slope of the tangent line at that point, because slope will be changing constantly. If you change the point, then slope will change. So either it can be positive, negative, or zero. Okay, that we have seen the function. So depending on that, if you try to look at the three-dimensional case for two variable function, if you do the surface plot, then what is the meaning of the first order partial derivatives? They are the slope of the tangent to this curve. Actually, what is the curve? If you put y equals to k, so in the so y equals to k, for example here, so that is a line actually, but in three dimension this is a plane. So we have a plane which is intersecting. Okay, this is kind of this plane. So here we have actually one plane. So this is intersecting with this curve surface, and this blue curve that we are getting here, you get. So at any point P, we can get at any point P the tangent to this curve. So here you can see the tangent, the curve. Also here we have this kind of tangent on this curve. In fact, if you remember the previous lecture, we have seen the that this for this tangent line, the derivatives del f del x and del f del y are the slope for these tangent lines. So these are the tangent lines, okay, on this curve, and it will change its direction constantly as you change the concerned point. Okay. So now there is another concept called total differentiation. So what is the meaning of total differentiation? For partial derivative, what we do, we actually, out of these two or more variable, we change only one variable and all other variables are remaining constant. But in total differentiation, the increments are given to all the variables. So for a two variable function, z equals to f of xy, then if you try to think of this delta x and delta y increment in the xy direction. For example, here it is the x comma y is point is here, and then you try to increase x plus delta x and then y plus delta y. So on the surface, here maybe x comma y, then x plus delta y, sorry, delta x, and y plus delta y. So if you move from this point to this point, then how much change is going to happen for both? Because earlier we have seen that one is fixed and another is varying. But in case of total differentiation, we have this relation. So for z, we have this one, and for delta z increment, we have this relation. And now for this delta z is actually of this form. So this difference. And if you divide by this delta x and delta y, and if you try to make it adding and subtracting f of delta y on the right hand side of 3, then we have this relation. So now if you allow delta x goes to 0 and delta y goes to 0, then what happens? This delta x, if you remember, this will be the ordinary differential coefficient. You remember this delta x. Then this delta z will become dz, the small case, and this delta y, okay, this delta x will become delta x, and this one will become delta y. But since in this case y is fixed, here is y, you can see the y is fixed, so that is why it is changing only with respect to x. So that is why the derivative is partial derivative with respect to x. Similarly, we have partial derivative with respect to y. So this is a very important formula. You have to remember it. And how do we get it? This is just a simple derivation. This delta z is called total differentiation, or some textbook will refer them a differential of several variable. Okay. 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 These things we will discuss in the next class. So change of variables of x and y by any other variable. So if we have a parametric form, actually, it is like finding the chain rule. Okay, this is related to chain rules. So up to this, you try to go through this total differentiation by the definition. So that's how. If you have any doubt, you can ask me.